So today we're going to start talking more formally about functions and methods. We call them, you'll find that I'm just going to use the generic term functions. Methods is a term that distinguishes functions that are inside of a class, which is an object-oriented programming kind of thing. So in Java we call them methods, but in C we call them functions. You'll find that I'm going to call them functions, period, right? Because they're basically the same thing. It's just a technicality on where they're located. All right, so a function is a reusable unit of code that may take inputs and may produce an output. So note here that I'm saying that it may take inputs, right? There could be more than one input, but is there ever more than one output to a function? Nope. So think about a function in math, right? What does a function in math look like? So if we take our inspiration from math here, if I said that f of x, or f of x, is equal to x squared, right? There's one input to that, and here, let me go into code LaTeX mode here there you go. That's more mathy, right? There's one input here, x, right? What is the output? Well, sometimes you go, instead of saying f of x, you say y, right? X is mapping to one output, y. But can you ever, and of course you can have other functions that are going to be a multivariate functions, say f of x comma y is equal to x plus 2y, right? You can have a function that like that with two inputs. But is there ever going to be more than one output? No, because that's not a function, right? There is only ever one, at most, one output, right, to a function, just like math, right? Because what happens if you have two outputs? What happens if you have an x on the number line here that is mapping to two things, like this one and this one, right? In other words, you have, like, say, a circle or something like that. It's not a function because it fails what kind of test do you cover in high school for that? The vertical line test, right? If it intersects at 2 points here, that means that there are two outputs. That's not a function. That's something else. That's called a relation. And you will be eventually talking about relations. Yep, there we go. You will be eventually talking about relations when you get to discrete math. But here, it's just a function, so there's only ever one output. Okay? There are some languages that kind of claim to have more than one output. For example, Python, you can return two things, but you're not actually returning two things. What you're doing is Python is taking these two things and wrapping them up into one thing, containing these two things, and giving you back that one thing. And then it unpacks those two things for you in syntactic sugar. So there's really no such thing as a function that returns more than one thing. A function can return nothing, and that's perfectly fine. But you can also have multivariate functions. You can also have functions where there's no input here, right? What kind of a function would that look like? There's no input. It doesn't matter what x is. The value is going to stay the same. That's a horizontal line, which is a constant function. Right? You can have that in math, and you can have that over here in computer science too, right? All right, so why do we even do functions? Well, we kind of gave a preview of why you want to do this, because if you have one piece of code that is repeated multiple times, not in the sense of a loop, but if you have one piece of code that you are like a square root function, right? There's a square root, I'm going to use it over here, I'm going to use it over there, I'm going to use it over there. Right? I'm not going to copy and paste a chunk of code that computes the square root. What I'm going to do is I'm going to put that into a function and then call that function, so that I don't have to worry about code redundancy. Right? It facilitates code reuse. Right? You don't have to copy chunks of code, and then you can call them. Right? And this goes with the dry principle. If you've ever heard that, the DRY principle, the don't repeat yourself. Right? So we don't want to have redundant code repeated everywhere. Take that code, package it up into a function, put it off over somewhere so that you can call that function. Another reason that we like functions is called, oh, go ahead, question? No? Okay. So another reason that we like, functions is for procedural abstraction. So I'm going to ask you, how does the square root function work? Right. Did you ever wonder that? Yeah. Did you ever bother to investigate? No, why? Because you didn't care, right? Who cares? We just want to use it. It's abstracted away from us. We don't have to worry about those details. Now, if you have to write that function, then yeah. Now I'm going to have to take a course on numerical analysis and look at a linear interpolation method, or maybe there's a Taylor series to do it if you have some calculus orientation. Maybe there's another way to do it. There are actually dozens of different ways of doing the square root function. Some with different properties, convergent properties, and some with other, other desirable properties. Maybe you want to look into those in detail if you've got an engineering question that needs to be answered. But at the end of the day, we don't care. We just want to use it, right? We simply want to use that functionality without having to think about the details of it. And that gives us encapsulation, right? So here's a term, encapsulating or encapsulate. We take that functionality, whatever it is, we package it up into this black box. The black box is not something that we ever look into, right? And that's why it's completely opaque to us. It's not transparent. And what we do is we then not worry about that anymore, right? We've got a function to do that for us. And once you've got that function, you never have to worry about those details again, unless you need to go back and answer those new engineering questions and mathematical questions of convergence properties, etc. Right? Not only that, but if you start doing standard libraries and external libraries, they come with a lot of testing, right? A lot of smart people have put in a lot of time into and invested a lot of time into making sure that they're correct by debugging everything, by developing test cases and test suites to give you an assurance that this code is correct. They've also gone through a lot of optimization. I'm taking a meta course right now at MIT on software performance engineering. Right? And there's a lot of, all the concepts that they're covering right now basically are taken care of by compilers, right? All of these little tricks and these bit hacks that can improve your code and make it so much faster. Guess what? A compiler can do that for you. So I forget who said it, but there's somebody who said that the premature optimization is the root of all evils, right? If you want to do some optimization, then fine, put that into a library so that other people don't have to worry about that. Put that into a compiler so that other people don't have to worry about that. You cannot hope to replicate any of these thousands and thousands of hours that have gone into this, right? So we're going to use standard libraries and external libraries as much as possible. But, I guess that this goes with another saying in computer science, don't reinvent the wheel, or we sometimes say don't roll your own, right? Maybe you do want to write your own square root function. Yeah, go ahead as an exercise. But at the end of the day, don't roll your own. Usually this comes up with cryptography. Don't come up with your own crypto system, right? Because it's bound to not be as good as those genius mathematicians that have discussed it and gone back and forth and poked holes in each other's ideas until finally the best ideas bubble up to the top, right? And it also goes down to basic problem solving, right? Here's a question. When you are faced with a problem, say a coding problem or any problem, what's the first question you should ask yourself?
What are we trying to?
What are we trying to? Okay, well, understand the problem a little bit more, but think laziness. This is why we're computer scientists. We like to automate things. We like to write software to do those mundane tasks. We don't like to work. Right? Has somebody already solved it? Exactly. Does a solution already exist? Does a function already exist in the standard library, or somebody has already put together a whole library, external library that does all this work for you, right? Or can an off-the-shelf solution be adapted, right? There was no round descents function when we were looking at that financial application, that loan application that we were doing before, right? We did the loan application, right? Or the loan amortization table application, all right? So I didn't have a round descents function, but I had a round function. What I could do is adapt that by multiplying by 100, calling that function, and then dividing by 100. I adapted that off-the-shelf solution so that I didn't have to do too much work. Imagine if you had to write your own round function. And believe me, it seems simple, but there are a whole bunch of corner cases that you have to account for, right? especially with floating point errors and stuff like that. So let's take a look at functions in C in a little bit more detail. As with variables, functions must be declared before you can use them. Let's go back over to this num primes example that we were doing last time. This is what is, come on, get rid of that. This is what is known as a function prototype. It's me declaring that there is this function called isPrime. It takes one input, an integer, and then it returns one Boolean, true or false. And I'm also putting documentation on top of this thing. That is a prototype. And so that's what we have to do in C. In C, you declare a function with a prototype. A prototype is a function, or is a function's signature. Function's signature. Right? What is a signature? It's identifier. That is the name of the function. Right? The type of variable it returns. Right? Or let me put that into code mode there. Returns. Right? And finally, any parameters or arguments or inputs to the function. Right? The number, this is sometimes referred to as the arity, right? And the types. Right? Is like integer, bool, double, etc. Right? So those three things go into its signature. Now, why do we call it the signature? Because it's our signature uniquely identifies us, or it should, right? Of course, people can forge signatures or whatever. But the idea of a signature is that it's a unique identifier. And it's not just the name of the function. It's also what it returns and the inputs or arguments that it takes. Those are called parameters. Right? That's why once we've declared a function like this, we cannot declare another function exactly like that. If I tried to do this twice, right, that's probably going to be at least a compiler error, or a warning, if not an error. GCC num, let's go with the wall flag. Okay, and the LM flag here. Oh, it actually worked. Why? Because they are not conflicting, but if I start conflicting there, probably it won't work. There we go. Wait a second, you have conflicting types here. Yeah, you can declare x and x again as an integer, but you can't do that with different types or a different return type over here. If I said that, oh, now it returns a double and it takes an integer, hopefully that this might be okay. Okay, good. Thankfully, it's not okay, right? But its signature is its unique identifier, right? Also, in general, the documentation of a function goes with the prototype. Right? With respect to that, you should use doc style comments, right? Just like I'm doing here. Remember the doc style comments / star star, vertical line of stars, and then an ending slash there, right? And DRY, right? You should not repeat documentation later on, right? When you actually do the function's definition, okay? Don't repeat yourself. Keep it in one spot, right? And keep it updated. Provide a description of what the function does and any expectations on its inputs. Right? For example, if you expect that x is going to be an integer, well, that's already given as part of the signature. But if I'm going to say that, well, x is greater than or equal to 2, this function expects that x is greater than or equal to 2. What happens when somebody calls that function and it's not greater than or equal to 2? That gets into something that we'll talk about after functions called error handling. What we'll do is we'll throw that, well, we won't throw it in C, but we'll return back an error code that says, you gave me bad input, don't expect me to give you any output, right? And that's error handling. That's something that we'll do later on. Right? All right, so after that, later on in the program, you provide a function definition. All right? The function definition has no semicolon, right? And instead has a function body, right? But remember that the signature is repeated, right? Because we already identified that there's this function out there called is prime. It takes an x as input, returns a Boolean, and so later on in the program down here, that's where we actually define what the function does. It has opening curly brackets, closing curly brackets, and anything you put inside of those opening and closing curly brackets, that's what the function executes when it gets called. Right? Once you've done this, once a function is defined, you can use it anywhere in the program. Right? Doing so, you invoke or call a function, right? And optionally, you can capture the return value, like we do with double y is equal to square root of x. We're taking the square root and we're putting it into the variable y. We don't have to do that. Come over here and let's go ahead and show. Let me show you an example. Yeah, let's go over to demo here. All right. So let me go ahead and create a variable here called x.